I would like to ask Eric Dean to come on. He's the Industry Relations at Texas State University and is going to be the moderator for our next panel. So please, panel, come up.
I figure if Llewellyn King can direct a panel sitting down, I was going to try it also. So thanks for joining. But Robert shared some amazing history and progress in the world of HPC. What he neglected to mention is his daughter was actually Offensive Player of the Year her junior or senior year as a soccer player at Texas State. So she was a big-time soccer player here, so way to go. All right, well, let me introduce our distinguished panel. We're very excited for the folks that came to share their expertise and thoughts. And as you saw, the microphone is open, so while we do have some questions prepared, we would welcome your questions as well. So let me start on your far left. Dr. Jakob Kornerup is from NI, the company formerly known as National Instruments. He manages the long-term innovation software team at NI. They explore new ways to test products and gather insights from large volumes of manufacturing test data. Previous roles at NI, he's worked on graphical system design tools for implementing DSP and communication systems on platforms like FPGAs, as well as representing timing and different models of computation. In the LabVIEW graphical programming language. He's a member of the IEEE 1588 Standards Committee for High Precision Time Synchronization, holds over 25 US patents around programming language design. PhD in computer science from University of Texas at Austin. And I didn't know this, he was assistant professor of computer science at SMU in Dallas. So welcome, Jakob. Next to him is Mike Schulte from AMD, and you heard Robert refer to Mike as the chief engineer on the Frontier and the LCAP exascale systems. He leads research, advanced development, and technology transfer activities in HPC, machine learning, heterogeneous systems, and power-efficient computing. Like I said, he's AMD's chief engineer on exascale systems, previously a PI on AMD's Fast Forward and Fast Forward 2 node architecture. Prior to joining AMD, he was a tenured faculty member at University of Wisconsin-Madison and at Lehigh University. He's an IEEE fellow, and I love his comment that throughout his career, he's had the honor of working with incredibly kind, smart, and talented people. So welcome, Mike. Next is Professor Tanzima Islam from Texas State University. She's an assistant professor in computer science at Texas State. Her PhD is from Purdue in computer engineering. Her research develops software and tools and data-driven analysis techniques to automatically identify performance problems of scientific applications running on HPC systems and how to mitigate them. The impact of her research on improving application performance has been recognized nationally and internationally through awards such as the R&D 100 Award, Science and Technology Award from Lawrence Livermore, and the College of Science and Engineering's Excellence in Scholarly Activities at Texas State. She's also a DOE SRP Fellow and a recipient of a recent research gift from AMD. So welcome, Professor Islam. And last but certainly not least is Jay Boisseau from Dell Technologies. And when I emailed Jay to ask if he would be willing to come to this panel, he said, "Do you mean an event with real people? I'm there." So welcome, Jay. Many of you know Jay. He's the AI and HPC technology strategist at Dell Technologies. He wears a lot of hats. He's the executive director of the Austin Forum on Technology, the Austin Smart City Alliance, and his work at Dell is just amazing. He evaluates new technologies and approaches for HPC, machine and deep learning, assesses customer workloads and needs. Currently, his focus is on cloud-enabled HPC for simulation and data analytics. And before coming to Dell in 2014, Jay led the TAC Center at UT Austin that many of you are familiar with. And a fun fact about Jay is that his doctorate is in astronomy from UT Austin. for his advanced computational research in modeling the structure of supernova explosions. And so,
Just type 1A supernova, not all.
okay, all right, a certain class. So welcome, Jay. So let's start off with a question. And again, if you have questions you'd like to ask any of the panelists, then we'll monitor the mic for you up here. But Jakob, could we start with you, and Mike and Jay, you might want to chime in on this. What applications of HPC is your company and I involved in that you're most proud of, and how also does HPC influence your company decision making?
So first, let me say that we technically don't use HPC as it traditionally is defined, but we definitely use, and our customers especially use, very scalable cloud computing for high volumes of data. We're in the business of selling measurement equipment that can generate tons of data, and typically that data has just been going away, but we are now seeing, our customers seeing the value and actually looking at that data and doing analytics on the data. And specifically in manufacturing, we have several customers who are in the semiconductor space who are using our technologies to optimize their manufacturing processes, testing every single chip and getting data from every single chip. And as you can imagine, that is a massive amount of data that you can actually do analytics on. So it is through there that we are seeing the growth of high-performance computing and the ability of scaling up to the computation you need to do in order to get your business decision done.
Very good. Mike, you want to chime in?
Yeah, thank you, Eric. So within AMD, we're both consumers and producers of software and hardware for high-performance computing. And so, for example, what we make, Robert, I think, did a great job of talking about it. We make CPUs, our GPU accelerators, and then also software that's used quite widely in high-performance computing. But then also we use high-performance computing in decision-making and chip design. So in order to build a chip, you have to do, large-scale electronic design automation. You have to go through a variety of simulation choices. And so we're, constantly using high-performance computing in order to make decisions about how do we build the best hardware, how do we go about optimizing our software. And then increasingly, we're using high-performance computing combined with things like artificial intelligence to make our products better. So not only adding enhancements to our processors to drive them to have greater high-performance computing capabilities, but also AI capabilities, and then building into the hardware things that leverage AI and data analytics in order to make smarter decisions.
Very good, Jay.
Sure, and I'll chip in and say, first of all, at Dell, we rarely talk as much about how we use the technologies as how our customers do. And so the one area I'll brag about is related to COVID. We have customers around the world that we've been working with, delivering equipment to quickly, configuring it, providing some consulting and advice on how to use it so that they could rapidly engage in this battle against COVID-19 in everything from understanding the epidemic and modeling the spread of it, understanding the genomic sequences in the virus, modeling the virus to try to understand how to develop therapies and vaccines to attack it, and more. We have customers around the world that are using high-performance computing in all of those areas and assisting greatly in this battle against this worldwide pandemic. An internal example I will give relates to the use of high-performance computing techniques in AI, in particular deep learning. Obviously, we want to sell the most reliable gear that we possibly can. A team led by Michael Shepard, Landon Chambers, and others at Dell used deep learning techniques to try to understand when there was a potential risk of some kind of failure in disk drive enclosures. And nobody ever wants their disk drive to fail, and by and large they don't, but they always seem to do it at the exact wrong time. There are some things that you can tell from hindcasting techniques like a database query to see if all of them came from the same manufacturing lot or were all shipped the same way. But there are other things that are much more subtle and harder to tell, and we wanted to be able to find not just the easy ones, but the hard ones, and to be able to make predictions about what set of conditions between which hardware, which software versions, which usage patterns, which data center environment characteristics like temperature could relate to an increase in stability so we could guide customers away from ever having these failures. And they found that their work was roughly 80% effective in predicting issues before they happen. So that was really interesting use of HPC-enabled AI.
Very good. Thanks a lot. And that actually leads to our next question. Jay, you touched on that it's your customers in different industries. Can you talk a little bit about the types of problems that you see different industries employing or leveraging HPC resources the most often?
Yeah, there's truly a lot of verticals and domains that use high-performance computing. And, you know, when I talk to my friends who aren't in computing, they don't believe that. They say, well, Alamo Drafthouse doesn't use high-performance computing, and Domino's Pizza doesn't use high-performance computing. I say, well, you don't think Domino's Pizza, Alamo doesn't yet, really, but Domino's actually does use high-performance computing to support data analytics. And many of the places that just because the point of sale system has an embedded processor doesn't mean the back office of the corporate headquarters isn't using very, very large-scale systems to do data analytics, machine learning, and such. But the verticals that are really known for being big in high-performance computing include government research labs, universities, especially R1 research universities, and all universities aspiring to be R1 research universities now. In the industrial side, we see it in manufacturing, oil and gas. We see it in the life sciences area. We see it in geosciences. We even see it in media and entertainment. You don't really think about, when you watch that Marvel movie, that those effects are not real. It's actors standing in front of a green screen because they're so good at photorealistic, physically realistic effects. But those are all calculated on a different configuration of high-performance computing equipment. So there's really, especially in the data era, no company of substantial scale that we don't see using HPC for, at the very least, data analytics and increasingly for training AI models. And of course, there's a broad set of engineering companies like in oil and gas and manufacturing and pharmaceutical design, automotive design, et cetera, that continue to use HPC for simulation of new products and new services.
Yeah, very good. Any other comments from panelists on the types of industries or problems that you see? Mike?
Yeah, so we've done a lot of really interesting stuff with the Department of Energy National Labs, and that's a really exciting partnership. They're looking at solving some of the nation's most important problems. So they look at things like, how can you build new forms of renewable energy? How can you fight COVID-19 and other types of infectious diseases by building the best medicine? They have some very interesting problems that they're working on for coming up with new forms of medicines and treatments for cancer, and how to be able to more efficiently personalize cancer treatments for individuals. And then also they're doing some great work in terms of overall modeling for climate change. So these are some of the key areas that we see in our work with the DOE National Labs. And then we also see a growing interest in data center use of high performance computing, where there's tons of customers, anywhere from people that are making diapers for children to the latest and greatest cars, automobiles, et cetera, where they really want to be leveraging high-performance computing, and increasingly high-performance computing combined with AI and data analytics in order to solve their problems. And a lot of the HPC is really based on modeling of either physical or chemical phenomena at very, very high fidelity.
Yeah, very good. I loved Robert's illustration of Siri, and that we all expect Siri to give us a response real time. And if it's not real time, then it's not going to be useful to us. So there's computing even behind that.
I wanted to add manufacturing. Yes. Manufacturing would be a big area. So cybersecurity, of course, nuclear security.
So for an industry that is making use of HPC.
HPC, yeah.
Okay, very good. Yeah, in your role as a researcher, so you mentioned manufacturing. Are there other industries that have approached you for problems that they're trying to solve in HPC platforms or performance?
So my work is in analyzing application performance modeling, and so forth. So I have worked mostly with the national labs. So their applications are in the nuclear security, in some of the things that he mentioned about health sciences. So those kinds of applications have come to me most often. as analyzing performance and so forth.
Right. Very good. Thank you very much. So we've touched on a few of the application areas, and let me launch into this question. How do you see high performance computing playing a role in AI, data analytics, digital twin modeling? I don't know if any of our manufacturing faculty are here, but that's a big area. And Internet of Things. Those are some application areas. How do you see HPC playing a role there? Jakob, do you want to start us?
Well, I think if you look at how a product's being designed, all the way from conception, all the way down to actually the manufacturing of the product when it finally is going out, all the steps along there, data is being generated. And the more you can generate insights from the data that gets collected at each phase, the better products you can deliver and with fewer defects out in the field here. But what's also interesting along that path is the use of digital models basically along the way, because we are seeing a tremendous amount of need for compressing the timeline from conception of a product to actually deliver to customers. And the only way you can do that is by creating these digital models ahead of time before you have physical artifacts you can actually work with. And so oftentimes you use those digital artifacts to actually speed up your testing, because you don't necessarily need to test on your physical devices because there's just inherent problems with getting the lifetimes, for instance, down in a reasonable time to get things into market. So for that we see customers using artificial intelligence as well as being technologies to kind of extract information from what they're doing with the data and see basically what should they do and what is the smart way to operate.
Right. Jay, this is kind of in your wheelhouse as far as AI strategist in your role. So what do you have to say?
Almost all of those examples you mentioned, I'd love to talk about for an hour instead of a minute. But
there is lunch right after this, by the way.
My usual long spiel on data analytics and AI is I point out that the only trends I really like to give are certainties. Humans always want to know what's happening and why is it happening, and what's going to happen next, why, and how can I make it work to my advantage. And that's, if you're a caveman wondering if the tribe across the river is going to attack or if the weather is going to be a risk to your tribe, to now in business and in national security, wondering what's the other guy doing, what's going to happen, how can I make sure I out-compete, out-innovate, out-win. And in this increasingly data-driven world, we use data analytics as much as simulation now to try to figure out scenarios. And it's awesome when we can use simulation, when we have the underlying physics well understood and we can simulate what's going to happen. But increasingly, we're trying to compete and innovate in areas in which we have vast amounts of data, but not underlying physical principles, at least not yet. And so we're using data-driven techniques along with simulation techniques. And since simulation is continuous math that we're mapping to discrete math, you really want arbitrarily large HPC systems, ever larger than we have now, even larger than at Oak Ridge. They're already planning their next one, I'm sure. So in simulation, you want more HPC, and in data analytics, it turns out you now want more HPC as well, because there's more and more data being generated. The computational power, even in an accelerated server, only grows so fast, but data collections are becoming enormous, and so again, you're needing the collective power of parallelism across these accelerator-powered servers in many cases to work on these very large problems. So HPC is not important in the inferencing part of AI, except for very high throughput inferencing from cloud providers and such. But for the training part, it's absolutely fundamentally important and will only increase in importance as we have more and more data to choose from in that. So certainly in AI and data analytics, just the raw data growth is making it possible for us to use more advanced techniques, but in return we need more data to make good predictions with all those techniques and more compute power to do it. So yeah, HPC's role in that is absolutely increasing.
I'd like to add one more thing, which is data-driven decision making, wherever we can say that if we can learn from this data to make a better decision into improving certain aspects of lives. So that's another area where, which is very high sort of computation heavy part of inference, not inferencing per se, but decision making. That's where HPC will be very valuable as well.
Yeah, very good.
That's where Domino's comes in.
Yeah, the things we don't appreciate, the HPC is doing behind the scenes. So without requiring an NDA for this audience, what can you tell us about new technologies that are going to influence or impact HPC performance? Robert, in his presentation, alluded to power efficiency, some other factors that are going to be an impact and that AMD is certainly looking at. So what are things you see as new technologies that are really going to help move HPC along? Jay, you want to start?
Sure. Robert hit on some of those things. Many things are non-disclosure. We can certainly, I do want to remind everybody that we've got some hardware people speaking today, but often the greatest enhancements are in software. So we talk about Moore's law improvement in processor, technically in transistor density, but in processor performance and such. We talk about exponentials and growth in data sizes, but it's often new algorithms that enable researchers, like to my right, to be able to do amazing things with this. Certainly you want more horsepower in the hardware, whether it's for simulation or for data analytics, but it's often techniques that make a difference. That being said, Dell is a solutions company, and a lot of that effort is on the hardware side, an increasing amount on the software side, but a lot is on the hardware side. And so we partner with lots of companies in the silicon space to see how they're getting more efficient use of silicon in terms of accelerators and domain-specific accelerators, how they're moving silicon into the network as well, smart NICs and DPUs and such, to try to move more computation closer into the network, closer to storage, et cetera. One of my favorite things, and there'll be a presentation at the Austin Forum on this in November, and it will hopefully be hybrid, so hopefully you'll come up to downtown Austin and see it at the library, but you'll be able to watch it on Zoom. It's quantum computing, and it's one of those things that, is it 3 years away, 5 years away, or 10 years away, or never? It's absolutely not never. We already use quantum mechanics principles in so many areas of life. We just don't know it because we don't call them that. Maybe the biggest disservice to quantum computing was calling it quantum computing, because it makes it sound mythical and magical and far out. But we understand basic principles of quantum physics for quite a long time, and we're just trying to figure out now the engineering ways to make this feasible, to make the systems have enough qubits, but also enough connectivity between the qubits and enough resiliency in that connectivity and of the qubits, so that we can do longer running simulations and then bring all those costs down. So if you think it's many, many years away, I'll tell you that global technology giants and massive countries on the planet are investing billions of dollars, not millions, not hundreds of millions, billions of dollars in this. It might be 5, it might be 10, maybe it's even a little less, but it's going to happen, and that's going to be something that lives alongside classical computing. It doesn't replace it. We don't have to worry about that, but it will be a different kind of accelerator that enables certain kinds of problems or algorithms within certain kinds of problems to be solved. So that's currently, to me, the exciting 5 to 10 year one, while we continue to make these improvements over the next 5 years in power efficiency, spreading silicon out through the system, and so on.
Yeah, Tanzima, your research focuses on this area.
Yeah, so I Googled to make sure that the information that I'm going to share right now is public domain. One specific name, so I'm in academia, so that means I don't always know what's upcoming, but one particular technology that I'm very excited about is the wafer engine from Cerebras. On one chip, there are 850,000 cores. And then 20 petabyte of memory bandwidth. That's what's one of the most important aspects of HPC workloads is the memory bandwidth. There's a lot of data movement that happens, so any chip, any technology that's coming up that can solve that memory bandwidth problem, it's going to be one of the technologies very important for HPC, and I just wanted to mention that. That's one of the things I'm very excited about.
Yeah, very good. Mike, Jakob, you want to chime in?
Yeah, so right now is an incredibly exciting time to be working in both architecture and software for high-performance computing and AI, because there are so many very, very interesting technologies on the horizon. So just as an example, within AMD, we've been combining our CPU and our GPUs together and leveraging the best of those technologies. Along with that, There's the ability to put very, very high speed, high bandwidth memory, in the same chip. Currently, we're doing that in terms of our GPUs. And then we see in the future that there's all sorts of opportunities for doing maybe more specialized accelerators. So if you, for example, are doing graph processing, there might be some good opportunities to build specialized hardware that's really, really good at those types of problems. I think another key thing that we're seeing is the growing importance of optimizing for data movement. And so, for example, silicon photonics or optical technology is becoming extremely important within the high-performance computing community, and figuring out how can you best move the data between different domains. I think also you want to minimize the amount of data that you need to move. So looking at things like computational storage, and we're in research at least looking at processing and memory. So how can you do processing on the data while it's still being resident in the memory system itself. And then in terms of memory technology, in addition to this very high bandwidth memory that we're now able to put within a package, there's also some very exciting non-volatile memories that are coming out that have the potential to have both very fast access times as well as extremely high capacities, because so much of HPC is becoming more and more data dominated. And then I'll just second what Jay had said earlier, that quantum computing we see as being a very important area in the future. We're not going to use quantum computing to solve everything, but there are certain types of key security algorithms, optimization algorithms, key problems in chemistry that quantum computing has an excellent opportunity of providing a great co-processor, you can think of it, for more traditional types of high-performance computing. And then finally, in addition to sort of the current work in, say, AI, there's also these neuromorphic processors that some people are starting to look at. So can you, for example, use some things that are more closely built on how the human brain works, and look at designing analog components within memory systems that allow you to more closely mimic the human brain in order to make fast, quick decisions.
Very good. Jakob?
Let me just add on from two sides. First of all, from the software side, I see the trend of writing much more modular, parallelizable code that is basically can work in a scalable way is the key to performance. And as Jay said, it's actually more important than the hardware performance, because if you write code like you did in the 80s and 90s, it simply won't scale up and give you the performance you need. So that's incredibly important. That added on with the technologies, somebody asked about virtual machines, but actually containers and things like that basically allows you to quickly deploy software in the right form and in a much more modular way than virtual machines and even physical machines give you. Those are kind of some of the things that I see on the software side. But then I want to go all the way over to the other side actually and talk about something Robert mentioned in his keynote. This is chiplets, because I think there's actually something there where you can now actually design your system in a much more modular way and actually get much more customized technologies much cheaper, basically.
Very good. Yeah, there was a lot in Robert's keynote that speaks to how AMD is looking at HPC development in the future, so thank you for that. One thing you mentioned quite a bit, and you gave some stats on this, is power efficiency. And I know we're going a little off script here, but I know you guys can handle it. How are your companies, or how do you see technology addressing power efficiency? And I see my friend here, Dr. Ziliang Zhang from Texas State, who actually runs a power efficiency research effort, looking at green AI and green computing. So that's a big deal, apparently. Robert, you mentioned it several times. So what steps are your companies looking at as far as power efficiency in these large-scale HPC systems?
Yeah, so within
Mike, I'll look at you first. Yeah.
Okay, yeah. So within AMD, for example, one thing that we've seen is by, in the case of the Frontier supercomputer, just as an example, one of the ways that we were able to get so much more power efficiency was by having the CPU and the GPU work closely together. And I think both Jakob and Jay did a great job that it's not just the hardware, but it's also the software, and really designing the software working in conjunction with the hardware to extract as much power efficiency as possible. Within AMD, all the way from our embedded, our laptop systems, all the way up to the biggest supercomputers, we put a huge emphasis on power efficiency. Not only because it's really important for our customers, because it reduces the cost, but we also believe that it's incredibly important for the planet to have more efficient overall computing. And so we're looking at ways, how do you reduce the overall amount of data when your processor is not running? How do you very quickly put it in a low power state and then manage it so that you can very quickly ramp it up to a higher power state? And then if there's certain components within a chip that aren't being used, how can we either efficiently power click gate or clock gate them so they're not using power if they're not doing useful work?
Yeah, very good. And that brings up a question. Professor Zhang, yeah.
Yes, since Eric called my name, so I would like to share a couple of stories about this, right? In 2015, I was invited to go to EPA. The Energy Star program manager, Catherine, invited us to go have a discussion with a group of industry talking about, Energy Star has been very successful to label the laptops, computers, right? Even now the washers, all the light bulbs on that. But software, can we label software with Energy Star, logo on that? We had a discussion in 2015. So at that time, the conclusion was too early. Software system was very complicated compared with hardware industry. So this year, I would like to share some good news. In Europe, they have the Green IT Coalition. They formed in March this year. Green Software Foundation was formed by Microsoft, GitHub, Accenture, ThoughtWorks in May 2021, and then Texas University is already joined as the first university academia and joined the industry. So we're working closely with the industry on the software design, how to improve the energy efficiency of the software. So the other thing I would like to share a story about, I teach 3 green computing courses in our university for undergraduate, master, and PhD degrees. So I did some experiments. So I found that, for the CS1 student who just learned programming, I tried to give them a program so that at the beginning, they are not trained on how to improve energy efficiency of the program. So they submit the code just for correctness. Your code works, give the right solution on that. So then I teach them how to improve the energy efficiency of that. So I compare the energy consumption with the first version and the second version. The difference could be 100 times different. So that just shows the students get excited because now they get a feeling about, how do I improve the energy efficiency of that and reduce the carbon emissions about that. So just a couple of stories to share about this. So a lot of exciting work to do. I'm excited to see the tide for the green computing, green software that is coming.
Yeah, thank you very much. And I think there'll be great follow-on discussions on that topic, certainly. Jay, how is Dell addressing power efficiency?
Sure. So as Mike mentioned, the silicon makers are trying to make the most efficient processors, sometimes CPUs and GPUs working in concert, sometimes domain-specific accelerators. Sometimes you need a general-purpose CPU. Sometimes you need an accelerator to get to optimize that silicon's performance per watt for just what you want it to do and not for other things. So there's lots of work done at the silicon level. There's starting to be work at the software level about which algorithms give the best results per watt used by the existing hardware. One of the things that I've been very interested in for a long time, remember my background is actually astronomy, which really meant physics applied to a certain area as opposed to computing, and it drives me crazy that we do all this air cooling. I know why we do it. Turns out most data centers aren't submerged and so on. There's air in them, not water, and so on. So we deliver a lot of air-cooled systems, but increasingly we're delivering water-cooled systems. The first generation of technology is direct liquid cooling, where you have essentially a really sophisticated hydraulic system that runs to cooling things that are attached to the hot silicon in the system, and cool water is circulated into that. The water is heated up because the device is attached to the processor, and the hot water is piped away, is tubed away from it. We're selling more and more systems like that. But we're also looking at the next generation of cooling technologies. We have a partnership through our OEM team with Green Revolution Cooling. It's a company based in Austin that uses mineral oil submersion, and you can consider that single phase cooling. So you basically, instead of encapsulating it in gas, air, with fans blowing it, you're submerging it in a liquid. in this case mineral oil, that's chemically and electrically inert. You can move that oil much slower than air because the thermal capacity is much greater, and you can transfer a lot of heat away from these hot components using some of these different liquids. It's more efficient than gases. Now, without violating NDAs, as we look at roadmaps for silicon going forward, we see the possibility that even single-phase liquid immersion cooling techniques may not move enough heat away from future generations of silicons as the demand for performance increases. So you may have to combine the direct liquid cooling contact with the silicon with the slower but immersion technique, or you move to a two-phase technique in which you're literally picking special fluids that boil as they come in contact with the CPUs, are condensed, and the vapor is captured, recondensed, and piped back through the system. So there's a company in Dallas that Dell is working with in this area as well to explore two-phase cooling systems. So I'll let the silicon makers speak to what they're doing to give you the best performance and the best performance per watt. We're designing at the system level to try to figure out what some of the right cooling technologies and configurations should be to give the greatest data center efficiency at scale.
Yeah. Thanks. Question from the floor.
Thank you. I'm all about power efficiencies and coolings, but I also want to see what your take is on this. In the world of AI and its world takeover and human domination, do you see unsupervised learning as being the most dominant area of research in the future, as opposed to supervised learning and other methods? And if so, what does that look like in day-to-day life? How is that going to take place, implementation of unsupervised learning?
I'll take a quick stab at it. One of the challenges is not having structured data. So all those websites that you're clicking on, all the squares in the image that have a stoplight in them or a bicycle in them or a fire hydrant, all those sites implicitly thank you for tagging their data for them so they can improve their training algorithms, because there's a shortage of tagged data in the world. I think the opinion, this is just one guy's opinion, not Dell. I don't pretend to speak for all of Dell on this, but I think the unsupervised learning has to become the dominant part downstream. I think we have a lot more, it's a less mature area, but if we want to build a world of autonomous things, and again, not everything will be autonomous, much AI will be used to augment human decision support as opposed to replacing it. But increasingly, we're going to see more autonomous things in the world. Some of them will be back-end processes, some of them will be in-your-face vehicles, all kinds of things in between. And for those things to really learn, I think we're going to have to improve our ability to do unsupervised learning in the field and pass that training on to other models and such. So I suspect that, I mentioned quantum computing in that 5 to 10 year window. I'm not sure unsupervised learning becomes the dominant mode in the next 5 years, but I can't really envision the future world of competitive technologies and products and services where people don't keep pushing forward and learn how to do unsupervised learning even more effectively with more efficiency at lower cost in order to outcompete and out-innovate each other. And even in national security issues, we know that the nature of attacks between nations, hopefully never, but could in theory, overwhelm human decision makers. So not just in industry, but even in national security issues, you actually want to be able to withstand the resiliency of failed communications between decision makers, of things happening faster than decision makers or troops in the battlefield can do. So there's not just industry, but government is also very interested in unsupervised learning as well. So that's my opinion on it.
Yeah, thank you, Jay. Other thoughts on that?
I completely agree. There's, supervised learning has been a dominant factor just because we wanted to start somewhere. But now that we're moving on to this, data lake, right? So there is data everywhere, but there isn't enough people labeling them. We can't just train, so we'll have to identify patterns, and that's why unsupervised learning is going to be the future. There is an intermediate step of semi-supervised where we can take advantage of some labeled data, a lot of unlabeled data, but at the end of the day, it's going to be, I don't need any feedback from humans. We can decide, in automation basically, would be making decision based on the data, which is not labeled, no one knows about them, but still, so yeah.
Yeah, thank you for that question. Hey, I want to change gears for my last prepared question a little bit, and we're sitting right next to a university with almost 39,000 students, which it's grown a little bit since the SWT days, I would say. So it's a big place. And in this room, there are faculty, there are parents, we've got kids in college. And what advice would you have for students to prepare themselves for this high-performance computing world, a job that's maybe helping develop or continue to advance HPC, especially since Mike was a faculty member and Jakob, you were faculty. What advice would you have for students? How do they prepare themselves for this HPC industry?
Well, so again, I think it starts with software, in my perspective. It is basically, you have to understand how to write good software that's modular, that is parallelizable and scalable, because that's the future. The second thing is the AI/ML angle on it. It is clearly a technology that you need to understand how to use, basically. Whether or not you need to become a data scientist or not, that's a separate discussion, but you need to understand the basic principles so you can really operate well in that. So those are the two areas I would focus on.
Yeah, I think it's a great question. I think there's lots of things to do to prepare students for high-performance computing. Completely agree with Jakob about, the fact that getting a good foundation in computer science can be extremely important. I think also having a good mathematical background, understanding algorithms if you're developing HPC software can be very valuable. If you're more on the hardware side, then I think it can be very valuable to, have a solid foundation and electrical, computer engineering, et cetera. But I'd also encourage students that are thinking about careers in HPC to go beyond the basics and the required courses, but take things that really interest you. Find out what you're passionate about, because there's going to be so many different applications for high-performance computing and artificial intelligence. So for example, if you're interested in music, make sure that you delve into that and you really understand not only how can you make beautiful music, but how could it be made better in the future. If you're passionate about sports, I think that's also an area where high-performance computing, artificial intelligence, decision-making can be made. And then I'd also like to add that in addition to the coursework, internships can be extremely important. So if you can get an internship in industry, in the Department of Energy National Labs, if you can do a research assistantship while you're working on your undergraduate or graduate degree, these types of experiences really take what you have in the classroom and they compound it, so you end up getting a chance to work on real world problems.
Tanzima, do you want to speak to the preparing students?
So how many students are there actually? Oh, there are, awesome. So I had prepared the actual course lists that would help. So the core courses in computer science, data structure, algorithm. And then system side, understanding how a system works, how software works, would be the type of courses such as compiler, computer architecture, computer networks, because that's what HPC is all about. There are millions of cores connected essentially, so we'll need to know how things move. And then more advanced courses, so Mike mentioned, go beyond just the required core courses, right? So that would be parallel computing. I mentioned compiler, so parallel computing, if you're interested about data science, then machine learning or that kind of courses, visualization, those would be some good courses to prepare for. One thing I wanted to mention and actually reinforce was work with and seek out research mentors in your department, people working on research. If you are not sure what you want to work on, then basically do an independent study with them. Professors may not hire you right away as an undergrad research assistant, but if you are interested in independent studies, and if you find that topic to be interesting to you, then you can actually continue to be a paid member of that group. So,
Very good. Jay, advice for students?
God, those were, I think they hit they hit everything. I guess if I was going to add anything, I'd say don't underestimate the importance of the math for the kind of high performance computing you want to do. If it's simulation-based science, most of us in the real world, we have to take calculus and then never use it again. But if you're doing simulation-based science, you will need to understand how differential equations are solved on a computer and how to map that to a computer and the algorithms, first order, second order, fourth order algorithms for doing that, explicit and implicit methods and so on. If you're doing more data science and AI, don't underestimate the importance of probability and statistics. In fact, I wish probability and statistics was required for every single person who posts anything about the pandemic on Facebook. It is really clear that this country does not understand probability and statistics and needs to be required learning for everybody. But if you're going to be in data science, you're really going to be using it. So don't underestimate the math.
Very good. Andreas, question from the floor.
Yeah, I don't know if this has been covered in any element or not, but I'm curious about the following. We're moving to this notion of, the cloud, and it's beautiful and it's wonderful and it's super secure and continues to scale. And with the kind of data centers in the cloud that are being built are amazing, and the way that the compute and the jobs, right, from graphics to everything else with dedicated chips has been growing. Do you see HPC moving from the cloud and the big data centers and potentially leveraging over time edge compute as it continues to grow, and eventually it's going to be in the car and the meter and the water heater and everywhere, and there will be hundreds of billions of computing machines idle waiting for something to happen? What are your thoughts on that?
Can I go first?
Please.
So I think Andres was asking about, as we see these big HPC systems that are on-prem, and increasingly people are using HPC in public clouds, which if you think about it, look a lot like on-prem HPC systems, rows of densely packed servers connected by low latency Ethernet or lower latency InfiniBand networks and so on. So in that sense, you should think of just cloud as a model for the way it's provisioned, for the abstracting of the applications from the hardware, and that the freedom that enables in terms of elasticity, of payment models, et cetera. But that you can just think of data center-centric HPC, whether it's on-prem or cloud. I think the question he was asking was, do you see in this era with billions of devices out there on the edges, do you see HPC moving out to edges? And the answer is, of course, yes and no. There will always be benefit to having certain kinds of algorithms run where latencies are incredibly small, you're running on very large data collections, you're solving increasingly complex physics models, multi-physics, multi-scale models, where you don't want to distribute those computations over geographical distances, which have orders of magnitude more latency than in data center latencies. On the other hand, we talked about autonomy out there in the world and more things doing more computation. We absolutely want more computation out in the real world because, for example, do you want Amazon to tell your car when to brake when someone's crossing the street in front of you, or do you want your car to determine when to brake? They're called autonomous vehicles for a reason. It'd be great if they're connected as well, but you don't want to rely on that connectivity in certain real-world situations where you must have autonomy. We mentioned battlefield sort of situations as well. So that increased desire to know what's happening and why, what's going to happen next and why, and how do I survive, win, outcompete, et cetera, means you're going to need more decisions closer to the point of action for the decision than ever. And that's an increasing thing. And that means providing more computational power at that point of decision, that point of action as well. So we're certainly going to see the high performance edge, and there'll be purists who say that's not really high performance computing. High performance computing is if you aggregated that into one. And others who say high performance edge is high performance computing. It's not an embedded processor anymore. It's got an accelerator, maybe even multiple. It's got high performance storage there. It can do some very powerful calculations there. So my answer is back to yes and no.
Jakob?
Yeah, and Jay can actually answer this question better than I can say, but this phone here probably corresponds to a supercomputer sometimes in the 90s or 80s or something like that. It's just a reclassification thing, basically. What used to be a high-performance computer is now becomes closer to the edge, closer to the human. Think about what you need to do in an automobile to have it drive autonomously. All the sensors you have to gather data from and the decision-making you have to do in that car. That is high-performance computing as we saw it very, very few years ago, basically. It is incredibly computational intense to do these kind of things. So it's just a reclassification, and it gets closer and closer to us.
Yeah, very good. I think we got time for one more question, so if you can make it quick.
It's going to be a doozy, so
Okay.
watch out.
Oh my.
You said something important there about closer and closer and closer to us. And there's the marketing side of our businesses, and then there's the reality of the constraints of machine learning and what we profound say to be true artificial intelligence, like some sentient type of concept. I wonder philosophically, you mentioned bringing up what students should study. And in the philosophy and the ethics side of that, or philosophy side of that, how much opportunity or need do you see for humility and understanding what we're actually capable of doing versus what we're trying to say we're doing? And the difference between human replacement and human augmentation.
So just that little simple question.
Just that little simple question.
Yeah.
So,
It's easy closeout question.
I mean, yes, people need that. Those are great questions. There's great books. Byron Reese lives in Austin, wrote a book called AI, Smart Robots in the Fourth Age, or it has those kind of words in the title. It's Byron Reese, R-E-E-S-E. Fantastic book, and explores all of those kinds of questions, including the philosophical ones. People are going to be very pragmatic and say, okay, AI is whatever it can do for my company tomorrow, and then I'll worry tomorrow about whether it's sentient the day after. But I think those are really fun questions to talk about, and they help us understand some of the issues about bias and ethics as well, to remember what the limitations of these systems are, that humans are training the data, humans are developing the models, collecting the data, might even be biased in the way they're collecting the data without realizing it. I think most bias that's human-introduced bias is unconscious, it's accidental. I think most people are really good people trying to do work in this, and then we want to say, oh, ethics, bias, blah, blah, blah. But these are very important questions, especially in the era of autonomous machines, because right now our system for blame in a car accident is if your car hits mine, we determine, who was at fault there, and one of us gets blamed. But if your autonomous car hits my autonomous car in the future, our whole legal system is set around blaming people, right? And it's not a perfect legal system, it's just the best we've got in terms of trying to map to fairness and justice, but it has huge implications for other parts of society. It has implications for HR and how you conduct hiring practices and train your staff. It has implications for who you give mortgages to and how you decide on treatments for different candidates for different therapies. It's so hugely important open questions there, and I think this is where university space is really going to help us a lot, because frankly a lot of companies are going to worry about how does AI affect my next quarterly earnings, and can I do something different to improve the reliability of this? And that's important. You want that. You want Dell to sell you more and more reliable systems and whatnot. But I think right now that space is more, I'm going to defer to you, but I think it's probably more in the academic space, people trying to answer the next level questions about AI.
That's right. So that actually brings up an avenue, a newish avenue of AI and ML, which is explainable machine learning or explainable AI. So why did a model make that decision of, let's say, rejecting certain loan application? And then what can a person do to make sure that their loan application, which was, let's say, the decision was made by a machine learning model to reject, what can the person do to make sure they can actually fix something and apply for that loan and get approved? So we need more explainability from these models that we have traditionally thought of as black boxes. So that's a newish avenue of research where we are working on, and it's in the horizon.
Yeah, thank you for that question. And this sounds like a perfect lunchtime discussion. And with that, would you join me in thanking our panelists today?